Uncertainty and error analysis. In any measurement made, there are always uncertainties associated with the measured values due to limited instrument accuracy and difficulty reading results. The uncertainties may exist because of random errors, systematic errors, or the combination of both random errors and systematic errors. Knowledge of the non-exactness of a measurement is important, especially when trying to define how good or useful a certain result is. For physics experiments, we need quantitative words to describe how close a result is to the expected answer and how reliable or reproducible our results are. Significant figures. If we write our measurement as 12.35 centimeter, it means that we are sure that the measurement is between 12.3 centimeter and 12.4 centimeter. The way we write the numbers is related to what is known as significant figures. To give you some examples, 23.21 centimeter has 4 significant figures. 0.062 centimeter has two significant figures where the initial zeros don't count. 80 kilometer is ambiguous. It could have two or three significant figures. If it has three significant figures, then we should write it as 80.0 kilometer. When adding or subtracting measurements, the number of decimal places in the result should equal the smallest number of decimal places of any term in the sum or difference. As an example, when you sum 23.2 plus 5.174, you should write it as 28.4, which follow the least number of decimal place in the sum, which is 23.2, which has one decimal place. When multiplying or dividing measurements, the answer should contain the least number of significant figures of any term in the question. Suppose that we would like to find the area of the rectangular plate by multiplying the two measured values, 16.2 centimeter and 4.5 centimeter. The answer for the area should be written as 73 centimeters squared. In your calculator, you would see 72.9 centimeters squared. Uncertainty. The first type of uncertainty is about absolute uncertainty. It is an uncertainty that comes from the smallest deviation on the measuring instrument. For example, if you measure the length of an object by using a meter stick, the smallest reading that you can read from the meter stick is 0.1 centimeter. This is the uncertainty of the length. Therefore, to write the length of the object properly, so you should write it as 8.0 plus minus 0.1 centimeter. This is also true for electronic devices such as weighing scale, digital thermometer, and digital stopwatch. So you will apply this type of absolute uncertainty when you do part B in this experiment. The second type of uncertainty is about the errors involved in repeated readings. Okay, so let's say you have 5 trials and you get 5 sets of data from it. So to find its uncertainty, we are going to use standard deviation. Okay, so we apply an equation, okay, to find the uncertainty given by symbol sigma equals to square root 1 over n and the sum of di square, where di stand for the deviation. Deviation is basically the subtraction of each of the data with the average value. So therefore, the final answer, you should write it as the average plus minus its uncertainty. And you must take into account that the uncertainty and the average should have the same decimal place. So you should refer to the decimal place of the average and followed by the decimal place of the deviation. So these two must have same decimal place.
The third type of propagation is the propagation of uncertainty. When the operations involve adding or subtracting quantities, the errors incurred are obtained by adding the absolute uncertainties of the individual quantity. For example, if you have an expression d equals to x plus y minus z, the uncertainty of d is obtained by adding the uncertainty of x, y, and z respectively. So you will apply this concept when you want to find out the uncertainty of the mass of water when you do part B in experiment 1. When the operations involve multiplying or dividing quantities, the errors are obtained by adding the relative uncertainties of the individual quantity. For example, if you have f equals to x minus x times y, to find the uncertainty of f, so we will follow this equation, that is delta f over f equals to delta x over x plus delta y over y, where you have to find out earlier the uncertainty of x and y respectively. The same pattern will be used when it involves division, that is when f equals to x over y. So you will use this concept when you want to find the uncertainty of density when you do part B in experiment 1. This is the experiment part of the theory that we have learned. Right. Basically, in part A, we are going to find the uncertainty of the oscillations by using a stopwatch. On. This is the stopwatch that we use. When you want to do your measurement, press start on the stopwatch. After 10 oscillations, you can press the stop button, and let's say the reading is 0.0922. So you can see how precise the stopwatch is, where it can calculate up to 4 decimal place. So in your data, you must include 4 decimal places for every trials. This is the main apparatus used in this experiment. Now let's go through the other apparatus. We have a meter stick connected to a retort stand, and then we have a spring. Then we have a total mass of 50 gram that will be attached to the spring. So when you attach the masses to the spring will displaced. This is the equilibrium state of the spring after we added the masses. To begin the oscillations, we pull the spring 5 cm downward and release. You will see that the spring will go back and forth. To begin the measurement, once the spring is at the lowest part, you press the start button. One oscillation is considered when from downward it goes to the highest point, and then it goes downward again. That is considered as one oscillation. So you wait until 10 oscillations, then only you press the stop of the stopwatch. Right. In part B of this experiment, we are going to find the density of water with its uncertainty. Right. First we need an empty beaker. We need to measure the mass of the beaker by using a digital balance. Before we use the balance, make sure you press the tare button, to reset the balance. Right. After that, you put the empty beaker on top of it and record the mass of the empty beaker. Record it in a table. Make sure to write the mass of the beaker up to 2 decimal places as shown in the scale. Before we pour water to the empty beaker, please take note that the smallest reading of the beaker is 50 ml. So this will be the uncertainty of the volume. But in your calculations, you must convert the unit to meter cubic. Alright. Now, Okay, you can see that before I add the water, the reading is 182.41 gram. So once I pour water, so please take note that 1 ml of water is approximately 1 gram. Okay, so we expect that after I pour 300 ml water, the mass of the beaker plus water is approximately 483.99. Alright. You may state the results in the table as shown. To find the uncertainty of the volume of water, you may refer to the smallest reading from the beaker used. To find the uncertainty of the mass of beaker and mass of beaker plus water, you need to look at the decimal place of the balance used. To find the uncertainty of mass of water, remember you need to do subtraction process. So kindly refer to the propagation of the uncertainty when you add or subtract between two quantities.